Machine learning models are being increasingly employed in a variety of real world settings. For example, machine learning models are being used to assess decision makers like doctors and judges in domains like criminal justice and healthcare. They're also being used to determine which applicants actually get their loans approved. In addition, machine learning models are powering recommender systems across a variety of popular platforms, including Facebook, Amazon, Goodreads, and many, many more. So basically, machine learning is everywhere today. Now, the next big question that we need to ask ourselves is, in which of these settings is model understanding really crucial? And model understanding can be absolutely critical, particularly in those domains and applications which involve high stakes decisions that impact the lives of millions of individuals. Examples of such domains include healthcare, medicine, criminal justice, financial lending, and many more. Now let's try to probe a little bit more deeper to really understand what exactly can model understanding help enable. To do this, let's consider some concrete examples. So let's take this example where we have an image which is input to a predictive model, and the predictive model correctly labels this image as a Siberian Husky. Now, if we dig deeper and we try to understand how the model is making this prediction, we might realize that the model is actually using the snow in the image to tag this image as a Siberian Husky. So, this revelation has basically helped us understand that the model is relying on incorrect or spurious features when making this prediction, and we might need to go back and debug this model and improve it further. So, model understanding in this case facilitates debugging. Now let's consider another example scenario where we have a bunch of information about a particular defendant, including her previous crime records, socioeconomic information, and so on. When this information is passed through a predictive model, the model might output a prediction which says this defendant is too risky to release. Now, if there is a judge who is trying to see if and how to leverage this prediction, the judge might not really get too much information from this singular prediction. On the other hand, if we provide a deeper understanding, for example, if we tell the judge what are the important features that the model is using when making this prediction, and in this case, that happens unfortunately to be features like race and gender, the judge might realize very quickly that this prediction is biased because the model is using features like race and gender when making this prediction. And the judge will most definitely disregard this kind of a prediction and will make his own decision in this particular case. So in this scenario, model understanding is facilitating bias detection. Now let's consider another concrete example where we have an applicant who has just applied for a loan. Now all the details of this applicant are being parsed by a predictive model, which in turn deems that this applicant is not ready for a loan and denies his loan. Now, instead of just telling the applicant that his loan has been denied, it can be super helpful to provide the applicant with more information. For example, to tell him about what aspects of his profile or application can he change to improve the chances of him getting a loan in the future. For example, in this case, we might tell the applicant that he should increase his salary by 50K and pay his credit card bills on time for the next 3 months in order to get a loan in the future. This will basically provide the applicant with a deeper understanding of what he can do and what he can work on. So, model understanding in this case helps provide recourses to individuals who are adversely affected by model predictions. Now let's consider another scenario where we have a bunch of patient data and the corresponding predictions as to if a patient is healthy or sick, which are output by a predictive model. Let's say there is a doctor who is looking at these predictions. She may not be sure if and when and by how much to trust these predictions. Now, if we provide her with a deeper understanding of what the model might be doing, in this case, the model might actually be using ID numbers to make predictions on female subpopulations, but it might be using the apt features like if a person has cold and cough when determining if a male patient is sick or not. If the doctor sees this and has this deeper understanding, then she can quickly realize that the model is using irrelevant features when making predictions on female subpopulation, and therefore she cannot trust its predictions for that particular subgroup at least. So in this case, model understanding helps assess if and when one should trust model predictions when making decisions. Now let's consider the other side of the same scenario where a regulatory agency is trying to determine if this model that we just saw is actually suitable for a more wider large-scale deployment. And looking at the deeper understanding or looking at the explanation that we have of the model, the regulatory authorities quickly realize that this model is using irrelevant features like ID numbers when making predictions on female subpopulation, and therefore is not really suitable for wider deployment at this time. So in this case, model understanding has allowed us or the regulatory authorities to vet models to determine if they're suitable for deployment in the real world. So model understanding is actually enabling a ton of use cases, including debugging, bias detection, providing recourses. It's also helping us understand if and when to trust model predictions, and also helping us vet models to assess their suitability for deployment. In enabling all these use cases, model understanding is actually serving a variety of stakeholders, including end users, for example, loan applicants, decision makers like doctors and judges, regulatory agencies like FDA, and also researchers and engineers to help better debug their models and make them better. Given that model understanding is enabling so many use cases, let's now turn to another question, which is how do we actually achieve model understanding? To this end, previous work has basically proposed two prominent approaches. The first approach is to basically build models that are inherently interpretable. For example, models like linear models or shallow decision trees or other rule-based models, which are often considered interpretable, as humans can actually look at these models and make inferences about how the models are making their predictions. Right? The second approach to achieve model understanding is to basically explain pre-built models in a post hoc manner. For example, let's say we either have a black box model or we have a very complex model like a deep neural network with several tens or hundreds of layers. These kinds of models can be passed on as inputs to explanation algorithms or explainers, which in turn produce explanations in the form of either linear models or shallow decision trees or other rule-based models or even visualizations, so that these give a more interpretable understanding to the end users. Right? So these are the two approaches that previous literature has advocated for. Now, the next big question is to basically think about when to use which of these approaches. So, when to basically go for inherently interpretable models versus when to go for post hoc explanations. To answer this question, let us basically consider an example. Let's say we are in a setting where accuracy interpretability trade offs are actually existing. For example, what we observe is that as we make our models more and more complex, we are able to get higher and higher predictive accuracy. For example, when we were using linear regression or decision trees, maybe accuracy is taking a hit. On the other hand, when we basically use more complex models like random forests or deep neural networks, our predictive accuracies are improving, right? So these patterns can actually commonly observed in certain settings, especially in things like image recognition and so on. Okay, so now there are certain settings where these trade-offs exist, and in those cases, we might not want to sacrifice accuracy for the sake of interpretability. And in such cases, we may want to rely upon post hoc explanations. To get a deeper understanding or intuition about when we might encounter these settings, let us now consider another example. So what you see here is actually a two-dimensional scatter plot of a data set. The data set just has two dimensions. On the x-axis, we plot dimension 1. On the y-axis, we plot dimension 2. And what you see is just a scatter plot of the data points there. And as you can see here, this data is actually linearly separable, which means we can actually build a simple interpretable linear model in this case, which will also be pretty accurate because the data itself is lending itself very naturally to these kinds of models, right? Because the data is linearly separable. Now let's consider another case or another scenario where the data has very complex nonlinear decision boundaries. In this case, simpler models like linear models may not really be able to capture these complex boundaries correctly, and we may need to resort to using more complex models for the sake of predictive accuracy. Right? So in this case, there is clearly a trade-off between going for interpretability versus accuracy because complex models might achieve higher accuracies. And in such cases, we might resort to using post hoc explanations. Okay. And there is also this scenario where sometimes you just don't have enough data to build a model from scratch, right? All you have is that you are just stuck with a proprietary black box. And in that case, also, we might want to resort to post hoc explanations because there is pretty much no other option. Now, in summary, what we would like to emphasize on is that if you can build an interpretable model which is also adequately accurate for your setting, please do it. Otherwise, post hoc explanations can come to your rescue. And this tutorial will focus on post hoc explanations.